some practice here with our solubility principles. All right, so we've got a couple of questions here. We're going to start with some definitions. So a couple of pretty important definitions. One is the idea of a saturated solution. All right, so a saturated solution, I might list a couple of key points. One, it is a solution in which no more solute will dissolve. And we can imagine that. That's your Kool-Aid mixture that you're making, from which you couldn't add any more sugar because it just pools at the bottom. All right, and we can get a little bit more detailed too. We can say that this is a solution in which the rate of dissolving is equal to the rate of precipitation. All right, so what I could give an example here. So the rate, let's say magnesium sulfate, which is the salt used in float tanks. And, so let's imagine that's a solid salt. And that will turn into magnesium ions floating around in solution and sulfate ions floating around in solution. So a saturated solution means the forward rate and the precipitation are equal. These are in equilibrium. So the forward rate and the backward rate are in equilibrium. And that's the last key idea about a saturated solution. So the salt and ions in solution exist in equilibrium. Equilibrium. Okay, so that's the first key idea, is that a saturated solution has some of these principles. All right, we could go into more, but that should be sufficient, I think, to get us started. All right, next, a solubility product. A solubility product is the equilibrium constant for a saturated solution. All right, and it has the abbreviation Ksp, and is usually a product of two ion concentrations. And I might do another example. So for example, for the Ksp for magnesium sulfate, so I might use the above example, MgSO4 solid, goes to some magnesium ion, which is aqueous, and a sulfate ion, which is aqueous. The Ksp is really equal to just the concentration of magnesium and the concentration of sulfate multiplied together. That should be sufficient. All right, let's move on to question 2. All right, question 2 is some kind of like fundamental practice. You're not going to get very far if we have trouble writing this solubility product for a typical salt. So we're going to start with question 2a. So we're going to start with a dissociation reaction. So barium sulfate, solid, dissolves into barium ions, which are aqueous, and sulfate ions, which are also aqueous. So the Ksp should be equal to just the concentration of barium times the concentration of sulfate. And that's it. We'll move on to magnesium fluoride. So magnesium fluoride dissolves into magnesium. It's aqueous plus 2 fluoride ions. That 2 is going to be important because that means that Ksp for magnesium fluoride is going to be, we're going to have magnesium ion concentration times the square of the fluoride ion concentration. All right, let's move on. Question C, 2C. We've got this silver sulfide solution, which is a solid, and that's going to turn into some 2 silver ions, or aqueous, plus a sulfide ion, which is aqueous. And we have this Ksp value, which says that, okay, concentration of Ag, which is positive, squared times the concentration of sulfide. And lastly, copper iodate. Iodate? I think that's the name of that ion. All right, so we've got copper 2, which is interesting. Okay. Guess it's not that interesting. It's just copper 2 at the end of the day. All right, and so it's going to turn into a copper 2 aqueous plus 2 iodates. And they have a charge of -1 and aqueous. All right, and so the Ksp here is going to be equal to the concentration of copper 2 plus times the concentration of your iodate squared. I'm going to put little boxes around all these so they're nice and easy to find when people are checking their solutions. All right, and so question 3 goes into a little bit more detail. They're saying, okay, maybe this is a good time for a highlighter. We have a solution in equilibrium, and we remember that a solution in equilibrium that's a solution in equilibrium, that's a saturated solution. That means saturated. Okay. And we have this precipitate of barium fluoride, and the solution contains some concentration of barium ions and some concentration of fluoride ions. And the question is, maybe we'll use a different color for the question. What's the Ksp? All right. So for question 3, okay, we should probably start with a dissociation reaction. Barium fluoride, which is solid. It's going to turn into some barium ions, which are aqueous, and 2 fluoride ions, which are also aqueous. Okay, so we can write a Ksp reaction, or sorry, Ksp expression, pardon me, which is going to say our barium ions times the square of our fluoride ions. And then we're going to just punch in the concentrations for each of these and get an actual value for our Ksp for barium fluoride, which is going to be 4.59 times 10 to the negative 2. I'm not going to include units because you might remember from our equilibrium unit that when we included units in our equilibrium constant expressions, things get kind of funky, so we tend not to do so. We can save that for first year chemistry if it interests you. All right, 4.59 to the power of negative 2 times 2 to the power of negative 3. And that all gives us 9.18 times 10 to the negative 5. And that is our Ksp. I'll put a little box around that. That's not so bad. All right. So question 4, last question, says a saturated solution. Oh, notice of silver sulfide. So notice the last question said a solution in equilibrium. And this one says a saturated solution, but those mean the same thing. All right, we've got silver sulfide, so we're going to need to figure out a way to write that. A lot of silver in this unit, I noticed. All right, so what do we got here? We have 1.6 times 10 to the negative 16 molar sulfide. That's not a lot. And also, oh my, these are very small concentrations, which tells me that sulfur sulfide is not very soluble. And we're asked to determine the solubility product for Ag. So instead of asking for the Ksp, they ask for the solubility product, but it's the same question, right? And oh, we did find what silver sulfide is. So actually we get to skip that step of looking up the common ions for these guys. All right, so we got silver sulfide, that's solid. That's going to go and form 2 silvers plus a sulfide ion. Those are aqueous. And so that means our Ksp is going to be equal to the concentration of silver ions squared times the concentration of our sulfide ions. Because our Ksp is going to be equal to concentration of silver, which is 2.6 times 10 to the negative 17 squared. This is going to be a very small number. And concentration of sulfide, which is 1.6 times 10 to the negative 16. Okay, let's see how small this is. This is... If you were wondering what kind of concentrations we're able to actually detect, we're not really great at detecting these sorts of concentrations, even with our best instrumentation. This is a very low concentration. Now, you could make a concentration like this pretty easily, but you couldn't detect it. All right, just by a series of dilutions. Okay. So 2.6 times 10 to the negative, 2.6 times 10 to the negative 17. And I'm just going to press equals before I square it to make sure that I'm not just squaring the last part, or the 17. Square that, and then times it by 1.6 times 10 to the power of negative 16. And that gives us an extremely small number. Our Ksp is equal to 1.08 times 10 to the negative 49, and that's our Ksp. Simple as that. All right, well, let me know if you guys have any challenges with those questions. Come see me during Flex.